In this demonstration, you will learn how to use FENSAP-ICE's ice shedding feature to simulate cracking and shedding of ice due to rotational forces. This assumes that you are already familiar with the basics of using FENSAP-ICE, including FENSAP-ICE Turbo. The ice shedding feature is meant only for rotating components, which means that the components coming in have to have some degree of rotational forces and velocity in them. The ice shedding feature is engaged by running a flow, particle impingement, and icing simulation. Click twice on your configuration icon to open up your icing settings. In the model panel, you will notice the ice shedding feature in between beating and body forces. It is disabled by default. However, you can enable it by opening up the ice shedding dropdown and selecting delamination and cracking. It works by linking Ice 3D to a coupled stress solver which solves for the cracking inside the ice. A couple of prerequisites are needed to accomplish this. The first thing being the ice surface interface, which tells you what the ice is adhering to, such as steel or aluminum. Should you want to template your own custom material, you can use the custom feature located in the same dropdown. This allows you to access a user-defined file, which is available upon installation of FENSAP-ICE in order to get a custom template for your normal and shear-driven adhesion strengths. The next step you need to do is select the crack detection criteria. It is recommended to set this criteria to principal stress for ice. Principal stresses are the maximum and minimum normal stresses on a particular plane. Principal stresses can be defined below in the ice material properties. Within that panel, you will have access to various properties such as cohesive tensile strength of ice, which is essentially your principal stress. If you were to use the fracture toughness option within the crack detection criteria, then you would modify the related option below. Fracture toughness is the critical stress intensity factor of a sharp crack where propagation of the crack suddenly becomes rapid and unlimited. The remaining options can be modified based on your experience with the tool. Young's modulus is a mechanical property that measures the stiffness of a solid material. It defines the relationship between stress, force per unit area, and strain, proportional deformation, in a material in the linear elasticity regime of a uniaxial deformation. Poisson's ratio is a measure of the Poisson effect that describes the expansion or contraction of a material in directions perpendicular to the direction of loading. The value of Poisson's ratio is the negative of the ratio of transverse strain to axial strength. The last option allows you to specify the density of ice in your simulation. The rotation speed option is currently on. This feature only works for rotating components and requires a centrifugal load to cause the cracking of ice. The rest of the settings will remain the same, as they're directly imported from Drop3D. An important note, however, you will have a total time of ice accretion, and one of the things needed for shedding is to define the time between solution outputs. That solution output frequency is what is used to go into the stress solver, whether the ice will crack or not, and how many pieces it will shed into if it does indeed crack. Therefore, within the option panel, you will specify the solution output and the frequency of that shedding interval. For example, if you have time between solution output set at 5 seconds and shedding at every 1 printout, every 5 seconds the code will evaluate the ice for shedding. If you were to then split this into 2 printouts, you will get a multiple of this output. It would only evaluate the shedding every 10 seconds as opposed to 5 seconds. When you run your simulation, you will end up with a typical graph similar to the one shown here where it displays the total mass of ice. The sawtooth-like characteristic of this graph shows the reduction in total mass of ice and the point where shedding has occurred. From this plot, you can see when the largest piece of ice was shed. This can be confirmed and quantified in the output log files, as you will see later in this demonstration. Within the viewing panel, you will have the ability to view some of the solution. Pressing on the View Ice button will give you the choice of viewing either the shed ice, maximum ice shed, or ice cover. Both shed ice and max ice shed are features that allow you to see the ice that has shed from the last solution. Opening this will show you the last shed ice solution. You can see features here that correspond to some of the ice that shed in previous time steps. Go back and select Max Ice Shed. This represents the maximum piece of ice that has shed. It is using the same resolution as the grid that is presented. In this case, our grid is coarse. However, you can do an overlay of the surface. You will be able to see the location where the maximum ice has shed and the size of the actual piece. You also have access to shed solution files. These are available within your Run folder. You have two files, swimsol and swimsol.shed. If you select a run that contained number solution files, you would have, for each instance of shedding, a different file that corresponds to the timestamp in which the shedding took place. In addition to that, you have the ability to look at a shed log file. An ice shed file is located within your Run folder, which can be opened with a standard text editor. You will end up seeing a summary of each shed event. It will also give you an ID for each fragment, with the center of gravity in terms of the radial location, including the mass at that location. It will also print out the total amount of ice that has shed, the largest ice amount, and largest ice fragment. If you go to the end of the log, you will see here that the largest ice that has shed was 6.75 grams and occurred at 50 seconds. The largest fragment that shed also occurred at 50 seconds. Finally, the total solution time was in the order of 100 seconds. Therefore, somewhere in between the largest shed took place. This feature allows you to easily generate animations to predict mass of accreted ice shed due to rotational and aerodynamic forces, account for surface adhesion, mechanical stresses, and crack propagation in accreted ice. This concludes our demonstration on how to use FENSAP-ICE's ice shedding feature to simulate cracking and shedding of ice due to rotational forces.